Okay, so what I'm going to do in this video is just one more example of an inverse Laplace transform that's going to involve the second shift theorem. So let's have a look at this one. We've got the inverse Laplace transform of 1 minus e to the minus 2s times 1 plus e to the minus 4s on s squared. So the first thing we do is we want to try and get this into a form which is recognizable to something that we've seen before. So let's try expanding. So 1 times 1, 1. Minus e to the minus 2s minus 4s minus e to the minus 2s plus e to the minus 4s, all on s squared. So that becomes Laplace of minus 1 of 1 on s squared minus e to the minus 6s on s squared minus e to the minus 2s on s squared plus e to the minus 4s on s squared. So utilizing the principle of linearity, we can say that the inverse Laplace transform of this whole thing is going to be identical to the inverse Laplace transform of each individual component. So let's work out the Laplace transform of each individual component. So for the first one, 1 on s squared, that's just going to be t, because the Laplace transform of t to the n equals n factorial on s to the n plus 1. So therefore, if n equals 1, it's going to be 1 factorial on s to the 1 plus 1, 2, and that's going to give 1 on s squared. So that's correct. And then if we do the inverse Laplace transform of e to the minus 6s dot 1 on s squared, we know that that's going to be equal to, it looks very similar to, because we've got e to the minus cs. And we said before that the Laplace transform of u t minus c, f of t minus c, is just going to be equal to e to the minus cs f of s, providing that the Laplace transform of f of t is f of s. And by implication, we can therefore say that the inverse Laplace transform of e to the minus cs f of s is going to be equal to the inverse Laplace transform of this, which is the Laplace transform of ut minus c f of t minus c. So an inverse Laplace transform of a Laplace transform cancels all Laplace operations, and we're just going to be left with a function of u t minus c f of t minus c. Yeah, and that's obviously providing that f of s is the forward transform of f of t. So now that we've got this in the form of e to the minus cs f of s, we can say that c, in this case, just write that here, c equals 6, and we can say that f of s is 1 on s squared. Well, we know what 1 on s squared is. That's just going to be t, because we worked it out over here. So we can say that this is going to be equal to u t minus 6. That's going to be the shift, and the function is t, and because there's a shift, it's going to be t minus 6. Yeah. Now let's do the next one. The Laplace transform of e to the minus 2s dot 1 on s squared, and that's going to be equal to u t minus 2 t minus 2. And the inverse Laplace transform of the final term, e to the minus 4s on s squared, is going to be equal to u t minus 4 t minus 4. Yeah, based on these principles. So now what we can do is write the function in terms of the transforms that we've solved. So it's going to be 1 on s squared. Well, that corresponds to t. And remember, this is really t u of t. Okay, and that just indicates that the function starts from 0, which is defined in the integrand of the definition of Laplace, because we know that the integrand is defined between the limits of integration of the semi-infinite limits, between positive infinity and 0. So since u of t is a function that turns the function off for values less than t equals 0, and turns the function on for values of t greater than 0, this doesn't change the function in any way. But it's very useful to write this, because now we can compare this and contrast to the other functions which turn off at a time when t is beyond 0. So just to describe what's happening here, just a little bit, what this is saying is that the function changes at different time points. We have different functions that are actually turning on at different times. But what we have to bear in mind is that once a function is turned on, it stays on. So t u of t means t turns on when t equals 0, and it stays on until t equals infinity. At t equals 2, we've got another function, t minus 2 turns on. At when t equals 4, we've got another function, t minus 4 turns on. But the other previous functions are still switched on, so we have to bear that in mind. So we can say that the function is going to be 1 on from here, 1 on s squared. Well, that corresponds to t ut. So ut t minus e to the minus 6s on s squared, which is this one, u t minus 6, t minus 6. And then minus e to the minus 2s1 on s squared. That's going to correspond to minus u t minus 2, t minus 2 over here. And then plus u t minus 4, t minus 4. And what we can do is that we can rearrange that to make the order logical. So we can say that's going to be equal to ut of t. And then when t equals 2, we can say minus u t minus 2, t minus 2. And then plus u t minus 4, t minus 4. And then the last one, minus u t minus 6, t minus 6. So now we have a better description of the functions as they're turning on and off. At 0, t turns on. At 2, t minus 2 turns on, but remember it's negative, so we have to subtract. At t minus 4, the t minus 4 function turns on. And at, when t equals 6, the t minus 6 function turns on. So if we were to think about this in the time domain, we can say when t is between 0 and 2, t, or f of t, must equal t, because no other function is turned on yet. When t equals 2, however, between 2 and 4, now we have f of t equals t, because that's on, but there's another function that's on. Remember, it's negative, which is t minus 2. Yeah? So we have t minus t is 0, minus 2 is 2. Now, when t equals 4, there's another function that turns on, which is t minus 4, up until 6, t equals 6. So we can see that f of t equals everything that came before, what is before, which is 2, because that's still on. But between 4 and 6, we've got another function, plus t minus 4. So that should be 2 plus t minus 4 equals t minus 2. And then for t is greater than 6, f of t is going to be everything that came before, which is now t minus 2. But we're going to be adding, and we're actually going to be subtracting, because this is a minus now, t minus, when t equals 6, we have another function, t minus 6, that's the negative. Yeah? So that's going to be equal to t minus 2 minus t plus 6. So the t minus t's will cancel, 6 minus 2 is 4. Okay, so if we were to think about what that looks like, what the function actually looks like, we can do a little plot. So we can say between 0, we've got 0, 2 to 6, so let's say 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, just roughly. So between 0 and 2, I like to do some kind of scale. So between 0 and 2, f of t is going to be equal to t. So we're going to get this kind of forming here. And then between 2 and 4, it's going to be 2. It's going to remain at 2. And then between 4 and 6, the function is going to be t minus 2. So it's very important when you have a function, when you have a break in the function, always evaluate it at the breakpoints. So you've got at 4, 4 minus 2 is 2. So it actually is going to start over here. And then at 6, it's going to be 6 minus 2, which is 4. So it's going to kind of go up to here, kind of thing, just about there. But it doesn't have to do that. So sometimes you can have jumps. Sometimes the next part of the function might start over here or under here. And then for t is greater than 6, it's going to remain at 4. So it is a nice kind of confirmation. It's going to be 4. It's going to be 2. So there we have a physical graphical representation of the function f of t for the inverse Laplace transform that we started with over here.